cannot exceed, that is the limit, or that is the limitation that you have got. You cannot exceed against the upper limit of most efficient packings. So we were stuck at the maximum coefficient of conversion of around 50%, because that is the highest you can go. After that or beyond that, you get precipitation, macroscopic phase separation. And this is what you see in the intermediate stage, the blue phosphotungstate that is being precipitated, which is recovered, and the white thing is your polystyrene emulsion or the latex. And you phase separate it, and then you can reoxidize it, and then you can form the starting oxometalate again and do the catalysis again and again. And below it, you see the sizes, the different sizes of polystyrene microspheres, which looks from microspheres to nanospheres, which looks quite uniformly distributed. That means the polydispersity in the size is low. So we are able to control the size in a reasonable way. We changed gears. We went to the molecular regime, and we thought, what happens if we would add some acid into it and do the reaction with excess of styrene? This was the work that was done by Shontu Daksh, my student, with Dipti Lai, another very gifted undergraduate student of IISER Kolkata. So what they found out is that using these catalysts along with the one which we have been talking about, they were able to do or carry out a tail-to-tail coupling of the styrene together with the concomitant oxidation of the resultant adduct. So I'll not go into the details. So we have done all the details. If you are interested, you can have a look at this. So what we did again was to control the chain length of the oxometalates by using soft oxometalates, the chain lengths of the polymeric units. And we were able to control the polymeric units by changing the lattice spacing in these type of hydrocarbons, which are tablets. Now I'll talk about the shape changes. You start with these linear rods of heptamolybdate, and then Shontu and Preeti, they found out if they would irradiate it with light, then what happens is that you have a change in the shape of the particles. That is, from the rod-shaped particles, you have spherocylinders, and there is a concomitant change in the color. What is the reason for the change in color? We also found it out. You have heard it, that it is from the IVCT charge transfer bands that appears because of the reduction of the molybdenum 6 centers to molybdenum 5 centers in this type of species, which induces curvature and forms these ring-like species, which we checked from Raman spectroscopy and resonance Raman spectroscopy, and then we were able to find these type of spherical units. If we leave them in the open air, then they get back to the starting material, they get oxidized, and we can run this loop again and again, and we have done it almost quantitatively, what is the extent of conversions. We were able to show, for example, taking a host guest material, the kegging entrapped in a Keplerate. You have heard about Keplerate from Craig. So kegging entrapped in a Keplerate and sonicating them. So just by sonicating them, we were able to make length scale differences. That means we were able to make these rods, which were much larger than that of the cylinders, and then we were able to stitch the rods by adding small amounts of iron 3, which gives rise to this type of donut-like structures, and we monitored them in detail with EDX and with microscopy, and we were able to show that you have a competition of length scales that leads to the formation of different types of structures. Why we did that? We are interested in doing selective catalysis with different shapes that we have got so far. Then exploiting the interaction between the oxometalates with light, we joined hand with our physics colleague Oyub Banerjee and Mala Reddy was also involved, and this project was primarily being created in my lab by Preeti Thomas. And what we saw is that it is possible to induce shape changes, or rather it is possible to induce phase transitions in the oxometalates. How do we do that? So what we do is we take optical tweezers. Optical tweezers are nothing, but here we are not using optical tweezers in the true sense of tweezing. We are using them more in the thermal sense. So we would like to prefer to call them as thermo-optic tweezers. So what happens is that you have in these thermo-optic tweezers some very focused beams, very focused laser beams. So when you have these very focused laser beams, then what you do is you shine your laser in the sample chamber, which is given here, and because of the ligand metal charge transfer, the soft oxometalate creates or takes up a lot of energy. It creates a very small bubble, which is shown here. Now, as you have more and more absorption of light by the soft oxometalate, it starts to grow, it starts to expand. And the kinetics of expansion of this tiny bubble into the big bubble follows Oswald ripening kinetics or Oswald ripening regime, which means that if you plot the log of hydrodynamic radius against the log of time, you end up with a slope of 0.33. This is very typical of Oswald ripening. So we found that you have an Oswald ripening regime and you have formation of this big bubble. There was another interesting thing that was happening as well. What was that? That was you have a convection current that is going on here. That means the soft oxometalates from the cooler part or from the colder part were moving to the hotter part, or in other words, the hotter soft oxometalates, they were having two options as this convection current continues. Now this convection current is very similar or is known as the Gibbs-Marangoni convection current. Now where do you see this Gibbs-Marangoni convection? It's very simple. If you have seen, for example, a glass of wine, and if you swirl this glass of wine, you see, if it's a good wine, you see legs or tears of wine coming along the glass wall. So this happens because of the differential diffusion coefficient of the alcohol with that of the water. And as a result, you have condensation of water, and that leads to the formation of droplets, which slowly condenses and comes down the glass, and you have evaporation of the alcohol, which leaves the glass. So here we have similar current. This is the convection current which we see, and you have these type of convection currents, but at the base of the bubble, which is having the highest temperature, there it has two options. What are those two options? Number one, it can move with the beam of light, or number two, it can undergo a phase transition. That means soft oxometalate going to crystalline polyoxometalate. And indeed, we find that the soft oxometalate undergoes a crystalline phase transition, which we see from Raman spectroscopy. So where we see the molybdenum oxygen branching with molybdenum, this band completely disappears, and we have a molybdenum oxygen terminal stretch that appears. So we have a clear phase transition from the tubular soft oxometalates to crystalline polyoxometalates. And then if we move the bubble, then with the bubble, if we move the laser, then with the laser the bubble moves. And then as we move the bubble with the laser, we are able to see phase transitions and thereby formation of controlled patterns because of the deposition of the polyoxometalates. And this is how we were able to write the patterns, right? And we were able to put carbon nanotubes, we were able to put pyrrolic tetracarboxylic acid and so on, and we were able to write patterns as we would like to have it. Now this is all good. we then thought, can we combine it with some specific applications? Of course, this is a very proof of the principle kind of thing. So what we did is we took the soft oxometalate, the heptamolybdate, and combined it with tetraphenylphosphonium. Now when we combined it with tetraphenylphosphonium, we were able to form the soft oxometalate porous organic framework composite material, which in turn we could monitor from the zeta potential measurements. It shows an unstable regime, and then it goes to a stable regime and stays there. Now from the zeta potential measurement, when you have the stabilization, usually you have stabilization in the order of around 20 to 30 millivolts. So basically what happens is that if you have a charged particles, now this is something important for example, for the undergraduates. So if you have sand and you take sand and you put them in water, what happens? Sand precipitates, right? And you have the water. But if you could cut down the sand particles in size, make it smaller and smaller and smaller, and if you can put some charges on it, then they start levitating, that is floating, right? They don't precipitate. And they don't come close to each other because they have similar charges, so they repel each other. This is exactly the method by which one type of colloidal stabilization operates, right? And this is known as the charge stabilization. So that means the colloidal particle has a charge. This charge has a window of distribution of the charge from the surface of the colloidal particle, which usually follows Poisson-Boltzmann distribution. That means you have an exponential kind of decay of the charge from the surface of the colloidal particle, and then you have the stabilization. So as an experimentalist, how you find out whether you have stabilization or not, it is by measuring the potential, that is the zeta potential. So it gives you a measure of the charge on the surface of your particles, which you can find out by concomitant laser light scattering, right? So this is how we were able to find the zeta potential. And this zeta potential has a certain window, the window within which you have certain stabilization. If you cross that window, you have destabilization or instabilities. So we were able to find the window of stability, and this was done by Preeti Thomas, and then she was able to do it together with collaboration with Wen Thang of Jilin University and of course our manager. So Thang Wen of Jilin University, they are very good at making these type of tetraphenylphosphonium polymers. Now these polymers, they are polymeric material and they have complementary charge. So what we did is to form a polymer colloid complex. So one of the interesting things, as we were having a discussion with Craig, he was pointing out that it would be nice to have a molecular view of these type of polymer colloid complexes, because then we have insights more on the molecular region. Now, one of the limitations of these type of soft oxometalate is, for example, which we are facing right now, is that we are having problems with the colloidal, with the understanding of the molecular mechanisms, because we are all looking at the colloidal phenomena. Anyway, that's a separate story. So what we found is that we are able to form these type of patterns, and we did line scans with transmission electron microscopy. Now what is line scan in transmission electron microscopy is when you have a small particle like a nanoparticle, and if you see them with microscope like transmission electron microscope, then you have, because of the impingement of the electron beam on your particle surface or on your material, you have emission of the corresponding X-rays because of the excitation of the electrons from one shell of the element to the other shell. These particular emissions are then collected and are typical of the elemental composition which constitutes that particular particle. And in this way, you can even quantitatively find out what is the composition of your particular particle. and we were able to do a line scan, and you can see the beam damage that was done in course of this line scan. And you can see that we have all these different materials, all these different elements: phosphorus, carbon, molybdenum, and oxygen. So carbon is this one, it goes up, and then molybdenum is this one, it goes up, and phosphorus, molybdenum, carbon, and oxygen. And we were able to show that it is possible to do this simple catalysis, benzaldehyde-benzoic acid, and we were able to monitor this by Raman spectroscopy. And we could see again another heterogeneous kinetics that is in operation. So what was interesting is if we do the catalysis on the trail, we do see heterogeneous kinetics, but if we do the catalysis away from the trail, that means away from the surface of the active material, we do not have any catalysis. So that means it is very, very site selective. So we now intend to do more site selective combination of different types of catalysis on the chip. So this is to show the proof of principle, which you have also heard in this course of these GAN lectures. Two main problems, or three main problems, or three main aspects of catalysis. One is the reactivity, the other one is the selectivity, and the third one is the stability, right? So with stability we are fine. With reactivity and selectivity we have always a problem. So this is a way to optimize high reactivity with high selectivity, but in a bit artificial way. We were able, so Preeti was able to do it furthermore, and she did this oxidation of different alkenes in a similar fashion, and she could show again in a similar way that on the trail you have more catalysis, and away from the trail you do not have catalysis. So now we are trying to make conducting polymers using this technique by doping the polyaniline with the polydone states. Then what we would like to show is, for example, the future directions, or rather these are the present directions of our laboratory. So that is making the motors move, making soft oxometalates move. And this is what we have been doing. So Apabrita has been active in this area, and she has got some very nice results. So what we do is we take molybdenum 6 in the soft oxometalates, we reduce them with dithionite, we get sulfur dioxide. Then we have molybdenum 5 in the soft oxometalates. Now as we get sulfur dioxide, this sulfur dioxide creates an asymmetry in the distribution of the reactants on the surface. Because of the evolution of the sulfur dioxide, and also because of the shape of these particles, what happens is that you generate a slip velocity between the surface of the particle with that of the osmotic boundary or the reaction boundary. And because of this difference in the rate of evolution of sulfur dioxide with that of the surface of the particle, you create a slip velocity, which means the particle propels very tinily or in a very minute amount. And as the reaction goes on more and more, we have more and more evolution of gases, and we have more and more movement of the particles. We were able to do the kinetics, and we were able to find out the way how concentration of sodium dithionite changes with the velocity of these particles. We were also able to find out that it's possible to change the material, and we could do the motion, we could carry out motion of the soft oxometalates using hydrazine and evolution of nitrogen. Sulfur dioxide is toxic. You don't want sulfur dioxide to be used in biology, for example, right? It's very toxic. Nitrogen is less toxic. Nitrogen is more benign. So we switched from sulfur dioxide to nitrogen, and finally this would shift our gears, and we would enter into evolution of oxygen, and that is where we did water oxidation. So this is an experiment which is undergoing now, reviewing with the journal, and this is a collaboration with Ronojoy Odhikari of IMSC Chennai. So anyway, I will not talk about this in detail. I will switch gears, and you can see also assembly of different ensemble of the soft oxometalates, which reminds a little bit like the cacule, the movement of the fish of acule, which I saw in the National Academy of Sciences. So it is very reminiscent of the picture of collective motion. So the school of fish, it really looks like a school of songs moving on and on around. So now we switched gears and we took, for example, with the graphene oxide, reduced graphene oxide and oxometalate, we formed the soft oxometalate, and then we were able to do water oxidation. This is again another work by my former PhD student Chandu Dash and Otishmita Mishra, who is now working with Karsten Streck, who was an undergraduate student, now working with Karsten Streck in Ulm. So what they found out is that you have this composite, you have this entire material, and you are able to oxidize water into oxygen. And we are new entrants into these type of systems, so we made some mistakes and we learned it also a lot from the reviewers. So what we found, for example, that there was a pH-dependent change in the evolution of oxygen, and which we attribute to the stability of the cluster and the entire composite. And we do not 100% understand the reason or the role that is played by the graphene oxide, but we think it is responsible for the facilitation of the electron transfer. Having shown that, we found another very interesting result, same with the manganese phosphotungstate polyoxometalate when it forms SOMs, is that it does water reduction in addition to water oxidation. We did not publish this result. So what we thought, rather intuitively, is that it must be possible to couple it with water oxidation and carbon dioxide reduction. Now this is a work that has been done by Shubho, Shontu, and my former postdoc, Balaraju, who is now in Hyderabad. So this is, of course, this showed us that it is indeed possible to form the water, to reduce carbon dioxide into formic acid at the cost of oxidation of water to oxygen. Now, Craig has mentioned to you earlier in very detailed talk on solar fuels that the challenge, of course, is to do it in visible light. We are not there yet. So this has been done with UV light. So what we have done, or what we have shown, is that we have these three types of clusters. The MO154, the picture of which is here. Then you have the MO132, the Keplerate, which you have heard a lot about. And we took the Keplerate immobilized on a reduced graphene oxide interface, and manganese 6P3W24, which is utilized by us. So we took these clusters, we made soft oxometalate dispersions out of them, we shine light. Light creates an exciton, that is what we think. It creates a hole and an electron pair. The hole oxidizes water to form oxygen, protons, and electrons. These protons and electrons are transiently stored in this soft oxometalate, injected into the carbon dioxide to form formic acid. So we are able to reduce carbon dioxide to formic acid with extremely high turnover numbers. So the turnover numbers are in the order of 1.4 million. So it's one of the highest turnover numbers known for carbon dioxide reduction coupled with water oxidation. And we are having a recoverable, stable catalyst, which is shown here. For example, we get all the catalysts, those are stable and recoverable, and we can use them again and again. So we have used them over several cycles. Now what we are trying to do is we are trying to push this more towards more reduced products of carbon dioxide. So we would like to make, for example, methanol. And these are coupled with water oxidation, but the limitation here is that it works in the UV regime. But we are trying to push it towards the visible regime as well. So with this, I will not take much time. So with this, I would like to conclude. So what I have shown you, for example, is what we mean by soft oxometalates, what these are. We have talked about soft oxometalates in catalysis. We have talked about shape changes in soft oxometalates. We have talked about phase transitions in soft oxometalates. And then we have talked about different aspects or different possibilities of different possibilities of material construction with soft oxometalates, among which are artificial motors or autonomous motors, and then we have shown how we can do water oxidation and couple it with carbon dioxide reduction, and we are just on our journey. So as you may have realized that our focus is a bit on the catalysis, and we are striving to understand the basic aspects of soft oxometalates, which will perhaps unravel with time, but right now our main goal is to do soft oxometalate catalysis or photocatalysis with water and light and the salts. So with this, I conclude it would not be appropriate. I have not done this work, so all this work has been done by my very gifted group, all of whom these people are here, and some or not all, some of these people are here, and I would like to thank my collaborators. I have not shown some parts of work which have been done by these people, and thank you very much for your attention, and if you have questions, I will be pleased to answer. Thank you very much.
Is it valuable for other things like ethene to polyethylene, something like that?
Okay, so we have not done it, but I think it's very difficult because for that, for ethene to polyethylene and things like that, you need high pressure hydrogen at very high temperature.